Now I am going to solve the problem number 3 to create interest to use principle of mathematical induction. So the problem said that 1 over 1 into 2 plus 1 over 2 into 3 plus so on plus 1 over n into n plus 1 is equal to n over n plus 1 for all n belongs to n. Solution is that same step, let p of n is 1 over 1 into 2 plus 1 over 1 into 3 plus so on up to 1 over n into n plus 1 is equal to n over n plus 1. This is the statement Pn. So step 1, for n is equal to 1, what about p of 1? First we will take left hand side. So substitute n in the last element of this step, that is 1. In place of n we get 1 into 2, that is 1 over 2. And now taking right hand side we have n over n plus 1, that is 1 over 1 plus 1, that is 1 over 2. So we can say that left hand side is equal to right hand side. So P of 1 is true. Now we will proceed further, that is step 2. Step 2 states that we have to assume that the result is true for n is equal to k. So let the result be true for n is equal to k. That is P of k is equal to 1 over 1 into 2 plus 1 over 2 into 3 plus so on 1 over n into n plus 1 is equal to, replace n by k, and is equal to k over k plus 1, that is true. That means P of k is true. As P of k is true, that will imply that P of k plus 1 is true. So in step 3, we have to prove the result for n is equal to k plus 1. That is, we have to prove P of k plus 1 turn up 1 over 1 into 2, 1 over 2 into 3, plus so on 1 over k plus 1 into k plus 1 plus 1 is equal to k plus 1 over k plus 1 plus 1. Here we replace n by k plus 1. That implies 1 over 1 into 2 plus so on. Second last element will be 1 upon k into k plus 1, and the last element is k plus 1 into k plus 2, because this result comes out when we substitute n is equal to k plus 1. So a element before that element will be element when we put n is equal to k. So this is the second last element. which is equal to k plus 1 over k plus 2. So we have to prove this result. For this, again we will take left hand side, that is 1 over 1 into 2 plus 1 over 2 into 3 plus so on 1 over k into k plus 1 plus 1 over k plus 1 into k plus 2. So if we see that up to these terms, result is 2 in the step 2. So we replace this result by k over k plus 1 plus 1 over k plus 1 into k plus 2. That is again from step 2. If we see that, so proving step 3 is not difficult. So it is very easy to take step 2 from step 2 from the result second, and by the use of this result we have to prove P of k plus 1, that is also the principle of mathematical induction. If Pk is true, that implies. So it is obvious we have to use the second step result to create third step result. So it is not difficult to create the result of step 3. So we will take common out 1 upon k plus 1, and in the bracket we have k plus 1 upon k plus 2. So here we get 1 upon k plus 1, and here we get k square plus 2k plus 1 over k plus 2. So it becomes 1 upon k plus 1 into k plus 1 whole square over k plus 2. That gives k plus 1 over k plus 2. That is equal to right hand side result. So we can say result is 2 for n is equal to k plus 1. So as step 3 is proved, that is P1 is 2 and Pk is 2, and Pk implies Pk plus 1, that is Pk plus 1 is proved. So we can say that by principle of mathematical induction, Pn is true for all n belongs to natural numbers. So this was all about the third problem. Now problem 4, that is prove 1 into 1 factorial plus 2 into 2 factorial plus 3 into 3 factorial plus so on up to n into n factorial is equal to n plus 1 factorial minus 1. So we have to prove this result by the use of principle of mathematical induction. The solution is, first of all, let P of n is 1 into 1 factorial, 2 into 2 factorial, up to n into n factorial, which is equal to n plus 1 factorial minus 1. So this is our statement, that is Pn. So first step is, that is step 1. For n is equal to 1. What about P of 1? By taking left hand side, we get replacing 1 at the place of n, that is 1 into 1 factorial. 1 factorial means 1, that is 1. Product of 1 and 1 is 1. So now we are going to solve right hand side. That's it. 1 plus 1 factorial minus 1. That is 2 factorial minus 1. 2 factorial is equal to 2 into 1 minus 1. That is 2 minus 1 is equal to 1. Then we can say that left hand side is equal to right hand side. Therefore, we can say P1 is true. Now we will proceed to step 2. In step 2, as like other problems, we assume that result is true for n is equal to k. That is, P of k becomes 1 into 1 factorial, 2 into 2 factorial, up to n into n factorial is equal to, k into k factorial is equal to k plus 1 factorial minus 1 whole. That is, P of k is true. That is our assumption by principle of mathematical induction. So in step 3, we have to prove the result for n is equal to k plus 1. That is, P of k plus 1 means 1 into 1 factorial, 2 into 2 factorial, so on, k into k factorial plus the last step is k plus 1 into k plus 1 factorial is equal to, replacing n by k plus 1 in right hand side, that is k plus 1 factorial minus 1. That gives k plus 2 factorial minus 1. So we have to prove this result. So again, take left hand side, that is 1 into 1 factorial, 2 into 2 factorial, so on, k into k factorial plus k plus 1 into k plus 1 factorial. So first case step, result is true for pk. So by using that result, we get here, that is k plus 1 factorial minus 1 plus k plus 1 factorial as it is. We get this result from step 2. So from here we can see that from these two steps we have k plus 1 factorial common, and we have here 1 plus k plus 1 bracket close minus 1 is outside the bracket. So here we get k plus 1 factorial into k plus 2 minus 1. As we know that n factorial is n into n minus 1 and so on. So here we can see that n minus 1 factorial into n is n factorial. Therefore, we can replace k plus 2 into k plus 1 factorial by k plus 2 factorial by the use of principle of factorial. So we can say that this is equal to our right hand side result. So we can say that result is true for n is equal to k plus 1. That is, P of k plus 1 is true. So by principle of method induction, Pn is true for all n belongs to natural number. So this was all about the problem number 4.